I'm Sai Venkatakrishnan. I'm a PhD scholar in the Department of Computer Science and Engineering in IIT Madras. This is part of the problem solving live sessions for the course Operating Systems Fundamentals. This is for week 4. The agenda of the live session is as follows. We will be discussing a few questions pertaining to your week 4 lectures that you would have studied, and by solving those questions we'll be going through those questions, how to solve them, and the concepts in the week 4 lectures, so that it would help you to answer the current assignment questions which are released on the NPTEL portal for week 4. You can unmute yourself and ask questions, or you can post the questions in the chat box also. Both are fine. Try to make use of these sessions, and ask any questions, ask any doubts where if you have in the video lectures or in the questions that I'm going to discuss. Okay. So this is the first question. Which of the following is maintained privately in each thread? Whether it's the local variables or global variables, heap, or process ID. So which of the following is maintained privately in each thread? So there are many. If you take a process as such, say this is like process P1, right? So if you take, say, process P1, and if you have a program, say like int main, and there are some local variables like int a something, and then you have some int star p equal to malloc, and outside the main function there is a global variable like int glb equal to 0 something. So in this case you have like local variables, you have a pointer which is pointing to a malloc region which is the heap, and you also have a global variable, right? So which of the following is privately maintained in each thread? That's the question. So in a process, if you see the process map, one section would be the data section, the next thing would be the code section, and then you have your stack and the heap. So the concept of thread is nothing but you have the thread executes different can execute different functions separately, uh, apart from the other threads. So like in the same process you can have multiple threads executing simultaneously, thread T1, T2 and T3. Each can be executing different functions, but the catch is all the threads would be sharing the same data section and code section. Right? So the global variables corresponds to the data section. So this won't be maintained privately for each thread. And similarly, the process ID as such is something related to the process, the whole process itself, the process P1. And all the threads are part of the same process only. So T1, T2, n number of threads you can create, and all are part of the same thread. So even the process ID is shared only, it's not maintained separately for each thread. And then you have the other two options left, that is the local variables and heap. Now if you notice, the heap as such should be mostly shared among all the threads. It won't be different for each thread because the heap as such is part of the is shared among all the threads. The local variables, that is the stack pointer and the registers and all those things, would be private in each thread. So someone has answered option A, which is the correct answer. So the local variables like int a, this would be private in each thread. Just a piece of information is the heap is usually not shared between threads. Sorry, it is shared between threads. It will be common, but in some cases The heap is also a software, right? It's just like you have a library which is running this dynamic memory allocation. Say this call to malloc. So if you get to know about heap internals, what you can do is you can, up to some certain extent, you can have a different heap for each thread. So you can have a different heap for each thread. So this is like usually done for performance reasons, because when I'm going to access the same global variable or the same heap memory, which is shared between multiple threads, say 3 threads, then there has to be some sort of synchronization. So if say T1 writes to some variable in the heap and even T2 tries to write, then there should be some sort of synchronization. So to avoid all these overheads, the heap might be separate among all the threads, but this is usually done for performance reasons and is not common. You have to enable some options. So for question 1, the correct answer, the local variables should be privately maintained for each thread separately. Even if you create hundreds of threads, it will be privately maintained. Each will have a separate copy of the local variables, since the local variables are maintained on the stack and the stack is separate among each thread. It's privately maintained. So any doubt in the first question, you can post it in the chat box, or you can unmute yourself and ask your doubts. Right. In that case, I'll move on to the second question. Okay. So so we have the set of remote procedural call activities labeled P, Q, R, and S. The question asks us to rearrange the activities according to the timeline in which they occur. So which the step 1, step 2, step 3, and step 4. In that order we should rearrange. So anyone guessing, or anyone knows the answer? Whether which occurs first, which step? Since instead of looking at the options, let's go this way. Out of P, Q, and RS, which step 1? So in a remote procedure call, it's nothing but you have say two processes, say P1 and P2, and P1 is in a separate system, and P2 is also in a separate system. So let's name this system 1 and system 2. And now T1 has to send some information. It should call some procedure which is in P2. So like a remote procedure call. Now what happens, since these two systems are separate, you don't have a concept of like shared memory on the same system. So there is the concept of network sockets and all those things. And the advantage with using remote procedural call is you don't have to specify like explicitly use these network programming, like the socket programming and all those things. If you have come across in C or C++, you don't have to use that explicitly while invoking this remote procedural calls. The advantage with RPC is similar to say a function call. If you just write sum of something like this with in your C code or in your Java code, like a normal function call. This in the backend there will be like a third party library, like an RPC library or something, which should identify that this specific procedural call, this function call, is indeed an RPC, remote procedural call, and it will communicate over the network with the other system, the system 2, that's the acts as a server, and it marshals the data, that is sends the packages the arguments in such a way that the other system can easily read and sends it over the network. Now the other system will read those arguments, call the corresponding function which the remote procedure call intends to invoke, executes that function and returns back the result, right? So in this case, if we look at the steps given P, Q, R, S, the Q, the step corresponding to Q is step 1. That is, the client side stub locates the server. Say if P1 wants to invoke a function in P2, first P1 has to locate where this remote procedure is located, in which system, and also what's the IP address and all those things. So this the client side stub has to locate, and this client side stub is not part of the program that the application developer has. It's like a third party library usually. So once the client side stub locates where the external server is and how to communicate with it, next what it has to do is it has to pack all the parameters that it wants to send. Say if I want to send a calling a remote function, which is like say sum of 1, 2 and 3, and I'm passing like 3 integers, and these can be represented either in like little Indian or big Indian. Okay, so in that case what happens is, say if my system 1 is little Indian and my system 2 is big Indian, I cannot directly just send these arguments 1, 2, 3 just like that over the network. So what the client side stub has to do is it has to marshal. So marshal, in a sense, it has to bring all those arguments in a common format and send it across the network. So this is step 2. And once this is done, the server, on receiving the arguments, it has to first unpack all the arguments. It has to unpack that packet and all those things. So that is step 3. So unpack in the sense, this so usually while communicating over the network, it would be a kind of like a uniform representation. They would be using either a big Indian always or something like that. It can neither be big Indian or little Indian also. It can be some other representation. Say in some Microsoft services they use XDR or something like external data representation, those third party representation. And if your system agree on those representation, based on that the client side stub will marshal your parameters and pass it to the other system. Now the server should unpack those arguments and look at the specific function that the remote procedure is aiming to invoke, is trying to invoke, and should set up the stack and all those things and pass those arguments to the function. And also by unpacking, it should be stored in the memory in such a way that, say system 2 follows a big Indian notation, right? It should store the contents in such a way that it follows the big Indian notation. So this is step 3. And once this is done, it can execute the remote procedure. Say this sum is present in this process P2, this will be executed, and then the result should then be propagated back, again sent back to the process P1, which is present in the system 1. So this is step 4. So based on this ordering, if you look at the options A, B, C and D, we should have first Q is step 1, step 2 is S, and then we have R, and then we have P. So this is the QSRP. So option C is the correct answer, and someone has, yeah, C is the answer they have mentioned. Yeah, C is the correct answer. First, the client side stub has to locate the server. It should pack the arguments. Then the server has to unpack the arguments and find out which procedure it has to execute. Then the procedure is invoked in the server side, and it's executed and the results are sent back. So C is the correct answer. The other options are wrong. So any doubts in this question? How what's the advantage of remote procedure call? Uh, what are the steps, the brief 4 steps in executing a remote procedure call? Any doubts? You can post it in the chat box, or you can unmute yourself and ask. Right. We will go on with the third question then. So, big Indian and little Indian systems are, choose any one of the following: whether they both store the most significant byte first, whether they both store the least significant byte first, or whether they store, big Indian stores the least significant byte and the little Indian stores the most significant byte, or fourth option, big Indian stores the most significant byte and little Indian stores the least significant byte. Okay, so this big Indian and little Indian, say if this is your memory locations, okay, and it starts from address 0x00, and it stores like 1 byte in each location. So this is 0x01 and this is 0x02. And if I want to store the number 0x6, right? So if I want to store the number 0x6 in this, in the least address position, in a big Indian form, you will be storing the most significant byte. So if you get the binary notation of number 6 in hexadecimal, that is 110. Okay, and if you want to store, okay, let us, 6 is actually 1 byte, right? Yeah, maybe I can just add this like 6, 7, 8. Okay, so there's 3 bytes. Sorry for the confusion. Yeah. So if I want to store this number 0x678, right, in big Indian notation, how will it be stored is the most significant byte, that is 6, would be stored first, and then 7, and then 8. And while reading, it will be like this is the most significant byte, and this is the least significant byte, and this is the big Indian notation. And in little Indian notation is just the opposite. It's the same addresses, okay, but you will be storing 8, 7 and 6. You will be, so this will be your least significant byte and this will be your most significant byte. So the ordering of the most significant byte and the least significant byte, those things would change between big Indian and little Indian. So based on this, you look at the options. Option D, which Sashikant had mentioned in the chat box, is the correct answer. That is, the big Indian stores the most significant byte in the first address position, and little Indian stores the least significant byte in the starting address position. Okay, in a later question towards the end of this lecture, we will see why some applications use little Indian and some applications use big Indian, right? um, yeah, this would be interesting to look actually. Okay, any doubts in this question, the big Indian and little Indian notation? Right. In that case, we will move on with the fourth question. Right. The question is as follows: select the correct statement among the following. One, whether it's multi-process creation is heavyweight. Second, multi-thread creation is lightweight. C, kernels are generally multi-threaded. And D, all of the above. Which one of the following statements are correct? Which option is correct? Any guesses? Anyone knows the answer? Whether multi-process creation is heavyweight or multi-thread creation is lightweight, or this statement, kernels are multi-threaded, or of all of the above. So let's look at one statement one by one. So statement A, which is multi-process creation is heavyweight. say if I want to one process is running P1, and if I want to do a fork for 100 times, what happens? Each time you would be one this system call. Okay, so there would be a context switch, and next for each of the 100 child processes, P2 to P101, 100 processes, the child processes, you should separately maintain a process control block. There will be a separate stack, code section, data section, and even the heap would be separate. And also the page tables. So if you later you will study about virtual memory. So the page tables also would be separate for these processes. Okay, and the address space. By page tables we mean the address space. So say like we have like a variable int a, like a global variable, and if this variable is present at some address 0x8000, writing to this address from P2 does not change the value of a which P1 has. So this a would be stored separately in process 1. The same at the same address, this a would be stored having like a separate copy in process 2, and similarly for all the 100 child processes, this variable would be maintained separately at the same address. There will be multiple copies and each of it is independent. And if any one of these processes have to communicate between each other, then you have to either use a shared memory or like a remote or even these the IPC, the message passing techniques like send and receive, those explicit techniques, all those things you should use, and usually those will involve a context switch, and again this would be like a performance over. So all these things, right, makes the multi-process creation heavyweight because it involves a lot of steps to generate to create multiple processes. So in that case, option 1 is correct. The creating multiple processes are heavyweight. So to overcome this thing, right, multiple processes, what OS developers have come up with the concept is threads. So in a thread, what usually happens is all the threads belong to the same process. You don't have to create new page tables and all those things. Okay, just a second. So say this process P1, if you want to create 3 threads or something, T1, T2 and T3, three threads you are creating, say 4 threads you are creating. So in that case, the code and the global variable data section would be shared between all the threads. So the shared memory you can use as a medium for communicating between your threads, and also the code section you need not duplicate between each thread. The only things that are duplicated is one, the stack, and the registers that you use, and these are very lightweight in nature. These two are maintained separately, and this does not have much overhead when compared to the whole process creation. So in that way, this creating multiple threads, okay, is very lightweight when compared to creating multiple processes. And also the page table would also be shared between these threads. You won't be having a separate page table. Instead, all these things would be in the same address space. So in that case, the threads are very lightweight, creating a thread, and the process control block and everything is also same. Because the thread is not a different process, it all belongs to the same process only. So even the B statement, that is multi-thread creation is lightweight, is also correct. So let's look at the final statement C, that is kernels are multi-threaded. So if you look at the same example, say process P1, and it's having multiple threads, 4 threads, and say if one thread is executing, uh, one thread is calling a system call, some system call like read or something, say thread 1, and thread 4 is also calling some other system call, say some system call like write or something, write system call, something like that. It has to write to some file f2, and thread T1 has to read some file f1. Now the kernel, if it's not multi-threaded, what happens is at any particular time it will be able to service only one specific thread. So either T1 or T4 only it can service. But generally for performance issues, to scale up the performance, to really give meaning for having these multiple threads, right, user processes, multiple threads in the user process, the kernels are usually designed in such a way that they are generally multi-threaded. So the kernel as such itself will be multi-threaded. So when say when T1 raises a system call, the kernel will issue a new thread, and it will execute that thread, say kernel T1, corresponding to this user process thread T1. So this kernel thread will be separate. It will be running a different that specific system call, and it will be responding to this thread T1. And when T4 simultaneously asks some function, some system call to execute, the kernel will again create a new thread, okay, and it will assign that thread to this user process thread for servicing the system call and returning back the result. So in this case, what happens is, say if this T1 thread calls some system call, and it due to some parameter passing, some long parameters are passed to that system call, and that raises a trap, and it is stuck in between. So it's just looping indefinitely or something. It does not mean that the other threads have to wait for this T1 thread to complete. Since the kernel is multi-threaded, it can just provide invoke the system call, raise a trap, and the kernel being multi-threaded, it will just create a new thread for servicing the system call, and this really improves the performance of your system, the usability, and all those things. Right? So it really improves the performance. And when you are running in say a web server or something, in all those cases, having a kernel, multi-threaded kernel, and also the user space, if it supports these multiple threads, right, it really increases the reliability, usability of your system. So the C statement is also correct. So in that case, all the statements are correct. So the correct answer is option D, all of the above. So yeah, so D, one student has answered option D. So D is the correct option. All the statements are correct. Right. So I've got Sashikant has asked a question. What's the difference between a trap and a interrupt? So a trap is nothing but when you are executing a program, say main, and you have a operation like int a equal to 1 divided by 0. So division by 0 is not allowed, like in some software, like an exception will be raised, like a software exception, but in this case you will generate a trap, say or in another case, let me take this example. In your normal like a 64-bit machine, what's the address space that is addressable? You, if you look at your pointers, right, int star a, usually like 48 bits out of the 64 bits, 48 bits would be addressable. In the case, right, in the case like 0x80000100 something like that. So 48 bits you can specify any value, and that address would be present, would be mapped in your page table or something, right? In case if you use more than these 48 bits, say you just mention like int star p equal to like a long 64-bit integer, some 0x fff something like this, all f's, okay, or something like that, all f's. In that case, what happens when you access that pointer star p? What happens is the hardware sees that this is like an invalid address, and it raises a trap. And by raising a trap, what it means is this is an error and it has to be supported by the, it has to be handled by the operating system. So in that case, it raises a trap. So in English sense itself, like the literal meaning you can take, while the program is executing, it gets trapped in between. There is an error. So that's the notion of traps. And if you look at interrupt, take the literal meaning of the word interrupt. Your program is executing, and someone is interrupting you in between. And what is that someone? Nothing but your IO device. So something external to your system, to your process, if it's interrupting you, then that's like an interrupt. Okay, and at that time the interrupt is raised, and the interrupt also there will be like an interrupt handler and all those stuff. So this is the difference between a trap and an interrupt. In your if you have studied in week 1 and week 2 lectures, you would have studied the concept of system calls, right? So anything what your process does, if it results in an error or if it wants to call the operating system, that's a trap. If anything comes external from your process, it's an interrupt. So if you are calling this, if you are invoking a system call, say read or something, you will have this instruction syscall. The syscall is nothing but it raises a trap, and the operating system will see that okay, the trap was raised, the program trapped because this instruction, particular instruction syscall was executed, and based on the arguments you are passing to the operating system will know which system call to execute, whether it's a read or a write or something. So that's the whole difference between a trap and an interrupt. So in interrupts, usually you will be coming across DMA interrupts, direct memory access, or even IO device interrupt. So to avoid these interrupts, all you will be studying DMA, all those things. So this is the difference between a trap and an interrupt. Any doubts in this? If the concept is clear, then we can move on to the fifth question. So select a incorrect statement out of the following. Concurrency is not possible without parallelism. Whether this is incorrect. The second statement, a parallel system can perform multiple tasks simultaneously, or a concurrent system allows multiple tasks to make progress, and option D, none of the above. So out of the following four options, which of the statements is incorrect? Any guesses? Anyone knows the answer? Option A. Okay, right. So let's see. So let's start with option B. A parallel system can perform multiple tasks simultaneously. Of course, yes. So that's what parallelism is all about. You have task, say process P1, you have process P2. In a parallel system, you will say in a multi-core configuration, you can run process P1 on core 1 and process P2 on core 2, and this will run separately independently of each other, and if there is some communication also, it can occur in between, like a shared memory or something, right? So this statement is correct. Next, coming to option C, a concurrent system allows multiple tasks to make progress. Let's look at this statement. So concurrency is nothing but say if you have process P1 and process P2, and your system, your kernel will be having the scheduler in the kernel space. Your OS operating system will be having the scheduler, and the scheduler, what's the main task of the scheduler? The main task is to, say you are having multiple processes, say P1 and P2, it has to ensure that the system is used fairly, and equal time is distributed between process P1 and P2 for computation. So this is the main aim of the scheduler, and what it can do is, one simple way of scheduling is like a round robin fashion. So round robin fashion, you can have, say, like 3 seconds each process can execute in a round robin fashion. So first, for the first 3 seconds, P1 will execute, and next 3 seconds P2 will execute. So if you look at the end of 6 seconds, right, you will see that both P1 and P2 have executed. So this notion, at the end of some time, some 6 seconds, you see that both P1 and P2 have executed, even though you are running it on the same core, say this like a single core machine, and it's not multi-threaded or anything. It's just like single threaded in a single core machine. At the end of 6 seconds, you will see that both process 1 and process 2 has made some progress. Even though like both have not been completed, it has made some progress, and it should seem that you are executing, you are allowing multiple tasks at the same time. But the reality is, within those 6 seconds, you have just time shared your system. 3 seconds for process 1 and 3 seconds for process 2. So this notion is actually called concurrency. It is running concurrently, one at a time, but overall if you look at it, all the processes and tasks are making progress. That's the idea. So even this statement is correct. Now looking at option A, concurrency is not possible without parallelism. If you look at this process P1 and P2, parallelism is all about, you have, say, multiple cores, process C1 and the processor C1 and processor C2, multiple cores, core 1 and core 2. In concurrency, you need not have multiple cores to make the processes progress, these multiple tasks to make progress. In a single core itself, you can very well time share your system, time share, and you can achieve concurrency by time sharing by having a single core itself without relying on multiple cores or multiple threads. So this statement that parallelism is required to make to achieve concurrency is wrong. So this statement is the incorrect statement. So in that case, option A is the correct answer. So option A is the incorrect statement, as some of you have mentioned in the chat messages also. The remaining options are all correct statements. Okay. Any doubts? Right. So in that case, we'll move on to the sixth question. When we have to use the same operation on a large set of data, which type of parallelism will fit the task? Whether it's data parallelism, task parallelism, or both will work equally, or this task, this whatever problem, the same operation on a large set of data, this cannot be parallelized at all. So which of the following options are correct? A, B, C, or D? For example, say you have a large matrix M cross N matrix. This is M rows and you have N columns. Okay, and in that case, in this case, assume that in your program you have to identify, you have to say print the even numbers present in your matrix. Okay, you have to print the even numbers present in your matrix. Now the code as such, what will you do? This will be like a for loop over M cross N. Okay, like a nested loop it will be there. There will be a nested loop and there will be an if condition whether checking it's like an even or odd. And if it's even, you will just print it. So this code is common for all the elements. And now say this mn is say like 1 million. M is 10 power 6 and n equal to 10 power 6, assume. So now what you can do, if you have to use the same operation as in the same code, it has to act on a large set of data. So instead of sequentially going through each element, right, what you can do, you can split the matrix into multiple uh, divisions. Say row column wise, I can split it column 1, column 2, I can split it, and for each column, what I can do, I can execute the same code independently. So this code should not have any dependency or something, right, between the columns. If I run the same code separately, like I can do like multi-threading, okay, or I can do data parallelism, right? It acts on the same code but on different data. So you can do data parallelism on this matrix, since it's the same code, but the data alone with whatever it's operating on differs between the threads. So this is a nice example of data parallelism. So instead of going element wise element in each row and column, you can split this code, you can split this matrix into n columns, and then you can n threads you can initialize, and each thread will be acting on each row. So thread 1 will be acting on column 1, thread 2 will be acting on column 2. So n threads for n columns. So on each column it will be acting, it will just be looping it, like, and you also you can just change this code also, you can change this nested loop into a single loop also in that case, because just like column wise, so you can change the code. So in also it the execution is much faster. So that is what data parallelism is all about. Task parallelism is when you have the same data but you have to run multiple tasks either on the same data or different data sets, but the code as such will be different. In say in one task you have to run even or odd, and the other task you have to run say Fibonacci numbers, identifying Fibonacci numbers. In that case, this even or odd can be task 1 and this Fibonacci will be task 2. So that is task parallelism. So in the question they have asked clearly, uh, which type of parallelism will fit when we have the same operation but on a large set of data. So the answer is option A, that is data parallelism. The other options are wrong. So any questions in this, any doubts in this question? Right. We will move on to the seventh question. If you have any doubts regarding the previous questions also, post it in the chat message or unmute yourself and speak up. Okay. So in which kind of buffering queue the sender never has to wait. So this question is all about this synchronization. You have the producer consumer problem, right? So in producer consumer you will have a sender, the sender process P1 and the receiver process P2. And if P1 is sending something to P2 and P2 is the receiver, some information it's sending. Um, so this is the producer and this is the consumer. Um, this is the consumer C. So now the sender P1, in which scenario it never has to wait when the buffering queue. So there will be a buffering queue at each side. So the sender will have its own buffering queue and the receiver will have its own buffering queue. So this is like a send buffering queue, this is receive buffering queue. Now, what should be the capacity of this queue if the sender never has to wait? Whether it should be 0 or whether there should be some length for this bounded capacity for this queue, or it can be of any length, or none of the options are correct. Any guesses which one is the correct answer? Anyone? Okay. So the whole problem in this producer consumer, the whole key point to note is whatever I'm sending to the consumer, the receiver side, right, it should be consumed properly. Okay. If the consumer is not ready to accept the items that whatever the producer is sending, then the producer has to wait for the consumer to finish executing and to start receiving the items. Okay, so in that case, say the consumer has can only is busy in some case, is busy executing something, and now his receive queue is full, as in he cannot the consumer cannot receive anything, it is preoccupied. It cannot consume anything now. It is busy. It's preoccupied in some other execution. So now the sender is waiting to send some information. Now if the buffering queue is of 0 length, what happens is it has to wait. Say the sender is executing some function, it has to send some information to the receiver, the consumer. But now the consumer is busy and so the sender cannot send that information. It has to just wait until the consumer is free and receives that information. So in a zero capacity, the sender definitely has to wait. Say in a bounded capacity, what happens? In a bounded capacity, say you have the send buffer queue is of size 3, it is bounded. Then in that case, what happens? Um, the sender can place at most 3 messages onto the queue. Yeah, say M1, M2, and M3. Up to 3 messages it can place on the queue, irrespective of whether the consumer is busy or not. Now, if more than 3 messages are present, if you have to place on this bounded buffer, then the sender has to wait until the consumer is busy. Say if the consumer is still busy and the sender is ready to send a message 4 also. In that case, message 4, he cannot place it on the buffer queue since it has only slots for 3 buffers, 3 messages. So in that case, the sender has to wait till the consumer is free and is ready to receive the message. In an unbounded capacity, what happens is this buffer queue is like of infinite size. It can keep on holding messages that the sender has to send, and whenever the consumer, the receiver side is free, these messages will be sent to the receiver irrespective. So this queue would hold messages and the sender can be assured that whenever the consumer becomes free, these messages should be sent properly, and the sender can continue executing some other function it has to execute. So in the case of unbounded capacity only, the sender need not wait at all. So option C is the correct answer. The other options are wrong. Okay. Any questions in this? Any doubts in this problem? Okay. If not, we'll move on to the If not, we'll move to the eighth question. It's already 7 o'clock. I'll just take another 5 minutes. Okay. Sorry for the delay. Just three more questions to discuss. In which message passing scheme combination we get a renderer? Option A, both a non-blocking sender and a blocking receiver. Option B, a sender is blocking as well as a receiver is blocking. Option C, blocking sender and non-blocking receiver. And option D, non-blocking sender and non-blocking receiver. Which of the following is a combination which we usually call a renderer? So by the term blocking sender and receiver or non-blocking, what we mean is, as we had discussed in the previous question, by blocking, if is blocking sender means if the receiver is not ready to receive any message, the sender has to wait till the receiver is ready to receive the message before continuing with the execution. Same way in the blocking receiver, if the sender is not yet sent something to the receiver, right? And if the receiver is expecting some information from the sender, it has to wait indefinitely until it receives some information. It cannot just continue executing some other code. So that's the whole notion of blocking. In non-blocking, what happens is there is no need to wait if the other side is unresponsive or something. So the sender or the receiver, it need not wait. And the usual case of this renderer, when this usually occurs is when both the sender and receiver are blocking. So if we take the literal meaning of renderer, it's nothing but meeting at some pre-specified time. So this is the literal meaning of renderer, and when this will happen is between two the sender and receiver is both has to be synced. Some type of synchronization should be there, and they should know, like, okay, so at this time the sender is going to send some information and the receiver should be ready to receive that information at the same time. So there should be this synchronization between the sender and receiver. So that's the whole type of the idea behind a renderer scheme, and in that case both the sender and the receiver should be in blocking because it's all synchronized. It knows at what time it's going to send information and it will be ready to receive. So the option B is the correct answer. That is, the message passing scheme in which we get a renderer is where the sender is blocking as well as the receiver is blocking. If either one is non-blocking or both are non-blocking, it means that it's not like synchronized, and it's not like a renderer type of message passing scheme. It's something else. So option B is the correct answer. The other options are wrong. Okay. Any doubts in this question? So renderer is nothing but when both the sender and receiver are blocking, it means they are synchronized, and in that scenario we call this a renderer. That's the point. Any doubts? Right. Let's move on to the ninth question. The ninth question, it's as follows: a parent process may terminate the execution of the children processes using the abort system call. When will the abort system call be invoked by the parent process for stopping the child processes? Option A, when the child has exceeded the allocated resources. Option B, the child is no longer required, the task is no longer required. Option C, the parent is exiting and the child also should be exiting. Or option D, all of the above. When will in which scenario will the abort system call be invoked by the parent process terminate the child process? Okay. So if you look at option A, when it exceeds the allocated resources, say the child is given some 4 MB or something like that of address space to work upon, and there is a limit, or and if the child crosses that allocated resource limit, then the parent is free to invoke the abort system call to terminate the child. Okay, so this scenario is correct. This scenario is correct. Now, if you take the second scenario, that is the task assigned to child is no longer required. Say, for example, the child is given a task to um, wait for some 10 seconds or something to execute a loop for 10 seconds continuously. And if the 10 seconds are over, that task is no longer required. And in that case, what a parent can do, it can raise the abort system call, and stop the child from executing continuously. Okay, so in that case, the task is no longer required and the child should terminate. So even in this scenario, uh, the option B, this scenario is correct. The abort system call can be issued. And option C, it's given the parent is exiting and the operating system does not allow the child to run if the parent terminates. So in a process tree, if you take, so you will have like the parent process P, there will be a child process, and this parent can have many children, so C1, C3. If this parent process itself is exiting, so in that case, in some operating systems, what happens is all the child process also should abort and stop execution, and this is known as like a cascading termination. So the main thing is, if the parent process itself is not there, then all these child processes will become orphans. It does not have a parent. And in that case, the operating system designer would have implemented something called cascading termination, where the abort system call would be invoked for each of the child processes, and all these things would be first aborted, and then the parent process would continue with its exit invocation. It will be exiting. So even in this scenario, the abort system call is invoked. So the correct answer for question 9, in what all scenarios will the abort system call be raised or be invoked, is option D, all of the above. So in all the scenarios, the abort system call would be invoked. Okay. Any doubts in this? So if in an exit system call, if you notice, this is something the process will be doing on its own. Say if it's got an error or something like that. An abort system call is something like the external process does to the children process, the parent process does to the child process, something like that. In those scenarios, the abort system call is usually invoked. P1 is trying to abort process P2. So that's the difference between the abort and exit system call. So if the parent process itself has to stop executing, it has to invoke the exit system call. If the child process itself has to stop executing, it has to invoke the exit system call. Okay, any doubts in this question? Right. We'll move to the last question then. Right. Which Indianness is better, Little Indian or Big Indian? So if you say this number 0687, and this is the address 0x00, 0x01 and 0x02. So these are the addresses, and in Little Indian how will it be stored? Here there will be 7, 8 and 6, and in Big Indian it will be 6, 8, 7. So this is how it will be stored, and the address is from smallest to largest. This is the order in which the address is increasing order in which the memory addresses are there. It's from 0x00 to 0x02, and this is the notation in which Little Indian and Big Indian notations are there, in which case this number would be stored. The question is in which notation is better, whether Little Indian or Big Indian, or both are equally good. It depends on the application. Any guesses which one is the correct option, whether it's option A, B or C? So option C is the correct option. Both of the above, that is Little Indian and Big Indian, both are performance oriented. It depends on the application. So for example, if you take the Big Indian notation and say if you want to compare two numbers, what's the easy way of doing? First you just look at the most significant byte. Starting from the most significant byte, you go till the least significant byte, and what happens is you can if you just look at the this first digit in the Big Indian notation 6, and if say some other number 5, 8, 7, if you just look at the most significant bit which is 5, so you can just compare these two alone, and you can easily tell this number is the greater version. This is 687 is greater than 587. So in this thing you are just looking at the most significant byte which is stored in the smallest address location. In the smallest address. So in those scenarios, right, in the way the algorithms are designed and all those things, for example, just looking at the most significant byte if you want to decide something, in all those cases Big Indian notation is preferred. And also in networking applications, Big Indian is preferred compared to Little Indian, because the Big Indian is the standard way of reading from left to right. If you just look at this number 687, in the Big Indian notation it's 687. That's exactly what we intended to store. But in the Little Indian notation, if you read the number from left to right from the smallest address, that is 786, that's not actually the value that we stored. The value is actually 687, but we are storing it in the reverse order, starting from the least significant byte to the most significant byte. So this Little Indian notation is mostly preferred for processors and all those things, the low level code in processor implementation. The reason being, say if you are having like a 8 byte integer, like an 8 byte number, and you want to store the same number 687 in 8 bytes. How will you store this? This will be 7, your least significant byte 7 will be stored in the smallest address, followed by 8 and then 6, and all these the remaining 5 places to fill up that 8 byte, it will be zeros. Okay, now if I want to convert this 8 byte into a 4 byte number, and I'm sure that the same number would be this 687 would fit in 4 bytes also. This is just 3 bytes, and this would fit in 4 bytes also. Now how will the hardware represent this 4 byte? Nothing but what it will do is it won't read these extra 0 bytes. Instead it will just read from this location. This location alone, it will just read and return it as a 4-byte number. So 0687. Okay. So what happens in that case is these zeros over here, it's just like the leading zeros and does not increase the number or change the meaning of the number. So starting from either this location if you read it, or from this location you read it, the number is same, that is 687 only. The number of zeros does not make a difference, and also the size or those things does not make a difference. So in operations like typecasting, those things are a lot easier when you read it in a little Indian notation. When the size of the integers, say if I want to cast from a 16 byte from an integer to a short int, in all those cases, they say this int a is stored over here, this 8-byte value, and now I want to convert it to a short b. And what I can do is the starting address of this can just very well point to this location. It can just be copied over here. This part can be copied as it is. So you need not compare to big Indian. Little Indian is useful in these scenarios, whereas big Indian would be useful in networking applications and those scenarios. So depending on the application, the little Indian or big Indian is usually chosen. Any doubts in this question? Any doubts in the rest of the questions 1 to 10 which we had discussed? You can post it in the chat message, or you can unmute yourself and speak. Right. If there are no other questions, we can then wind up the session. That's the end of the session. The session is recorded, and also we will be sharing the slides also. Yeah. Thanks for attending, and thanks for making the session interactive. Thank you so much.